Okay, have fun.
Thanks. So, thanks everybody for coming. This is my presentation. Some people knows me, some other people doesn't. So I will make like a quick introduction about me and the tool. My real name is Sergi Alves, but most people knows me as Pancake. I was born in Barcelona in '83, and I'm currently working as a mobile security analyst at NowSecure. I'm the author of Radar 2 and several other open source projects. I'm a sleepless hacker. I try to sleep few and code more. And I'm also organizing the R2Con Congress, which is a congress around the tool that I've been building, and there is a huge community around this tool. So I've been developing it alone for maybe 6 years, something like that, having really small contributions, but right now it's like really active project. There are like 5 to 10 pull requests every day, and so many like 800 users in the IRC, and a lot of movement and people doing YouTube talks in YouTube, also in different congresses, etc. So the community is quite huge, so it's quite okay to have a congress around the tool. So it's the first year of this congress was last year. It's the second week of September in Barcelona, and it's just a meeting point for meeting all the developers of the project and people who is contributing and users. So if you are interested in learning more about the project, or you want to learn more about the internals or contribute or make a talk, just everybody's welcome to join. Last year it was like more than 100 people in there, and there was some problems with the space because there was like not enough room for fitting all the people, so I had to put like 50 person out. And I hope to find a bigger place this year. One of the restrictions of the Congress is that it's a Congress for the community, so I don't want sponsors, I don't want marketing talks, I only want technical stuff, I only want hackathons, sliding talks and trainings. Last year there was 4-hour trainings, and I will try to make 6-8 hours trainings because some people was complaining about that, and they will be probably more than 3 days of Congress. So what's Radar 2? Radar 2 is the rewrite from scratch of Radar, also written by me. It's a free library and reverse engineering framework. It's built on top of a set of libraries, which provide an APIs, different comments, because there is a command line for using these libraries. And it allows you to use script and pipe different comments in order to extend the capabilities of this. So it tries to follow a lot of the Unix philosophy. So it tries to be orthogonal. This means that all comments can interact with the others. This way you can do more things in less characters and also in less lines. So some people compare this to Perl or the learning curve is similar to the JIT or Beam, for example. So at the beginning it's quite hard, but from my experience, after 2 days or 2 weeks, depends on the person, they get used to the command line and interacting with the tool. I try to focus on API and the command line, and there are some different tools which are written on top of these libraries, and there are bindings for several languages. So I did the Balabind, which is a tool who reads BAPI files and creates automatic bindings for Python, Node.js, Perl, Ruby, well, thousands of languages. There are some graphical user interfaces, but no one is as complete as the command line tool. There is also a package manager, which allows you to install plugins, dependencies, and other things that are not as visible as the main command line tools, because they are in different repositories, so this way it's easier to find them. And some of the development rules that I try to follow is that I try to always refactor everything, so I don't want to keep things to be like stuck for years just because there is some people using that. So if there is some bad design in there, it must be changed. So this conflicts a little bit with some commercial tools, which are the only alternative to this tool, because Radar 2 is the only open source tool that is that as complete as many other tools that are available in the market. So I don't want to make this commercial or closed source or anything like that. I want to be everything available for everybody. And I try to enforce the test suite. So there is a test suite which takes like 20 minutes to run in Travis. There are code reviews, really intense code reviews in GitHub. And we try to fuzz with different file formats, different command lines, different tools that are in the project in order to find vulnerabilities in there. We also do static and dynamic code analysis in order to find vulnerabilities in the project. And right now it's an 11 years old project. And since the Radar 2Con of last year, I try to, well, not try, I release every 6 weeks. I think that having a fixed time releases is very important for projects, mainly because it makes the milestones much easier to manage. So you have a very easy way to understand how much time some functionalities take to be implemented. And I've been trying different models, and I think that this one fits quite well for me. What this talk about? I will show some of the features of this tool. I will make some practical examples, but I will focus on one target, and this target is this device. So this is a TYTERA, which is a DMR tone saver. It's a radio transmitter that you can use for speaking with other people and sending messages and so on, but it's using the digital radio spectrum. There are so many clones, so it's different devices, but it's exactly the same shape by outside, but all the internals are the same. We can see that, for example, there are so many, all of these devices are Chinese clones of the same device. The TYTERA is the original one, and the price goes from 60 to 100 euros, so it's quite accessible, so it's not really expensive, and it's quite fun to play with that. So I don't have this device. I just took these examples for showing some of the functionalities of the tool. I didn't check any of that since 2 weeks, so I'm not really into the development of this. I mean, I think it's a really interesting project, but I just took most of the information from the Travis Goodspeed talks in YouTube and the article that he wrote for the proof of concept number 10 design. Okay, so the first thing that was confusing for me was that the keys are not following the HJKL order. So you have the OK in the left side, the cancel on the right side, and the JK keys are swapped, so the two arrows are strange for me. But anyway, so internally there is an ARM CPU. It's an STM32F4 microcontroller. It's basically an ARM Thumb 2 CPU based on Cortex M4. There is FPU, and it also provides some interesting instructions that are doing cryptography, like SHA, MD5, AES, triple-Ds, and so on. It handles 1 megabyte of flash memory, there is 192 kilobytes of RAM, and there is a HRC 5000 radio baseband peripheral. This is one chip which is handling all the radio managing thing. And there are also some mapped devices. I mean, in ARM devices, as well as other kind of CPUs, the way for accessing the external devices of the CPU are done by mapping those devices in memory. So you have some regions of memory that you can read and write registers from there. And when the MMU detects that you're accessing this address, it's basically sending the wiring this to the device. So instead of using input and output instructions, like maybe like in Intel CPUs, you use only memory access things. So this device is able to manage one LCD screen, 3 SPI ports, 4 UART, 3 I2Cs, etc. There is also support for USB and Ethernet, but this device is only managing the USB, LCD, and SPI and UART ports. Okay, so the Radar 2 tool aims to be a multi-platform, multi-architecture, and tries to be as compact and easy to install. So there are no dependencies for installing the tool. The commands are compact. You will see that every time that you want to do something, you have to type almost 1, 2, or 3 characters. So the commands are not like full English. If you want to print the disassembly, you will type P and then D, because it's printing disassembly. If you want to see the XDump, you will use P and then X, which is for printing hexadecimal. This can be confusing, and people say that, oh, I have to learn or remember a lot of commands. But this is not true at all. I mean, when you understand the logic behind the letters and the logic behind the structure of all the subcommands, it's quite easy to understand that. And also, if you append some characters at the end of the command, you will get, for example, if you append a question mark at the end of the command, you will get help. If you append an asterisk at the end of the command, you will get the output in rather comment. So, for example, if you are searching for some pattern and you append the asterisk at the end, you will get the results of the search in comments of Radar2 instead of text. So you can pipe this to another instance of Radar2 and import these search results, for example. Other interesting modifiers for the comments are the J suffix, which if you append the J, you will get the JSON output. So that's quite handy for importing this information or managing it from other tools. It's command line, there are visual mode, there is also a web user interface, and there are some native graphical applications. So okay, so if we do this, we get like if we type the Python this way using the hashbang, we will run a Python shell, which is have a communication channel with Radar2. You can initialize this way, and importing the R2 pipe module and loading it, you get R2 object, which have the CMD comment function, which returns the result of the command. So if you want to do things like executing a command and getting the result, that's simple. So for example, if you try to use I and then J, it will show the output of the information of the binary, which is I, and then the J command will show the result in JSON. So here's the result of the JSON document, which is describing the information about the /bin/s ls binary. But if you use a cmdj command function from the R2pipe API, we will get the same thing, but parsing it into a native object for the language. This works in several languages. I mean, for example, in Node.js is really fast at parsing these kind of documents. In fact, it's like, depends on the language, but it goes from 4 to 10 times faster than FFI. So using native bindings is slower than parsing JSON documents, because the native, the dynamic languages are faster than creating dynamic objects than using that by parsing all the FFI structures. There is a huge community, and I try to separate all the logic. So every library implements a different thing, and you can use different libraries for extending that. In fact, there is some people who is rewriting some of these libraries. There is some intent in rewriting some of those in Rust in order to be able to say that we are memory safe and there is no issues in the like race conditions or use of the free or things like that, that you can do that very finely static time. And it's really best customizable and versatile. I mean, you can change almost anything. You can, for example, if you go into the visual mode, and you will see that you can, for example, change the color palette. You can disable the bytes. You can, for example, if you analyze this and you get the graph, you can have different printing modes for the graph. There's the minimap. There is also the PDS, which is reducing the amount of information that you have in the graph. And you can also debug from here. You can also have call graph, etc. Okay, so those are some of the libraries that are coming with Radar2. Rbin and RFS are libraries which are used for parsing headers of binaries. This is, for example, all ELF, PE, DEX, Java classes, WebAssembly. There are so many file formats out there. And Rbin is the library who loads the plugins for parsing these file formats. So if you want to support an old file format, like, for example, the Nintendo Switch binaries or any other kind of architecture, you can just use Rbin for that. All the comments in Radar2 show the list of plugins that are related to this tool. So, for example, if you use Rabin2 and then you use the uppercase L command line flag, you will get the list of all the plugins that are supported by Rbin. Those are only the ones that come with core. You can configure and disable and enable plugins if you want to create some smaller build of the tool, or you can just install new plugins using the R2PM, which is the package manager of it. So here is the list of all the packages that are coming with R2PM. There is also the REO. This library implements an abstraction over the input and output, so it's able to load different files, and by files it means anything, because in Unix everything can be a file. So I want to use the same concept in Radar 2. And the thing is that you can load, for example, an executable. You can map it in a specific address in memory. You can then split this binary into different sections and specify some permissions for that, and you can map this in different regions. So you can simulate the virtual memory management of any process in any operating system without having to depend on all the logic that is behind the memory management of the kernel, for example. So this way you can, for example, map the firmware, map the bootloader, map the RAM, map the virtual memory mapped devices, etc. And EO, as I said, everything can be a file. So, for example, process is also a file. The RAM device of the entire RAM of the computer is also a file. There are kernel plugins, for example, for reading, writing kernel memory for that. You can read any other process memory. You can also use R2Frida to use Frida as a target for EO. So you will read and write memory of the target process who is running an injected Frida session, etc. So anything can be a file. Even a socket file can be used for that. So there is also ASM and RAnal, which is for analysis. And those two libraries implement all the logic of the architectures. There is assembler. There is also API for disassembling. It's using different plugins by default. It's using Capstone for disassembling, and assembling we have our own implemented assemblers from scratch, so that we try to extend the logic and the instructions when we need them. So there is also support for gas. You can use the GNU assembler. You can also use the NASM assembler as a plugin. You can also use Keystone, etc. And the analysis module allows you to emulate code using a seal that I will explain and show later. And you can also analyze code. So you can identify basic blocks, functions, references, etc. All the logic for the debuggers is also split in different libraries. So, for example, you have the register profiles, which are loaded by the RREP library. And the register profiles basically define the structure of all the registers in memory. So when the kernel provides you a list of registers and their state, you can just use the register profile, which is a map that you put on top of the memory, and you read and you know, for example, the values of all the registers. RBP does the same for breakpoints. So you can, for example, change the kind of breakpoints that you want to use. If you want to use, for example, in Intel, most people will use CC for software breakpoints. But there are also other kind of breakpoints. There is also memory managed breakpoints. There are also hardware breakpoints, etc. And RDebug provides the APIs for debugging everything. I mean, there is APIs for stepping, for continuing, etc. You can, for example, step using software stepping, also hardware stepping, depending if the hardware supports it or not. There is also the APIs for RSearch and RMagic, which are used for looking for matches. R2 embeds the libmagic from OpenBSD. I have found 2 vulnerabilities and I fixed them, already reported. And the same thing goes for RSearch. I mean, you can find for patterns, you can find for known file headers, and if you have a RAM dump, you can use /m for searching for magic, and it will look for all the offsets that match a specific file header. After all these things, there is also rutil, which is the base library on top of libc. So the only requirement for using Radar 2 is having POSIX. This thing runs in several operating systems. I missed Haiku, but it's also supported. So there is Linux, Windows, Mac, iOS, Android, QNX, and for architectures it supports so many. x86, MIPS, ARM, ARM64. There's also support for Dalvik, etc. And for file headers, you will see also a list here, since Plan9 and Flash files, etc. The most common use cases for this tool is, most people, when they start using it, is mainly for solving crack miss. But there is a lot of people using it for exploiting, also for analyzing malware. The same goes for analyzing unknown file formats that you have, like a firmware that you want to understand what's going on. You want to carve memory for recovering deleted files, for example, or things that are still in memory, like passwords, for example, or you can use it for bypassing or cracking programs. You can also use it for creating new protections for the software. Some people using also for finding vulnerabilities or debugging crashes. So as I said before, the R2 pipe is the most recommended way for scripting Radar 2, but there are also other ways for doing that. You can build Radar 2 with Mscripten, so you get a pure JavaScript build of Radar 2. And this works fine. I mean, there is no. I mean, it's always better to use like a native build of that. But you have the, for example, the sure. You will be sure that there will be no overflows that will affect the running of the program. But it's a bit slower and it takes some time for loading. But anyway, it can be really interesting, mainly for WebAssembly, that will be soon quite used in all the websites. And there are native bindings for all these languages, and then there is a R2 pipe. The R2 pipe provides synchronous and asynchronous APIs for running commands and getting back the result. And there are different transports. What I said before, what you saw before, it was just using two environment variables that are exposing the two pipes, one for reading, another for writing. But there are so many other ways for communicating, for talking with Radar 2. You can use TCP, you can use HTTP. Radar 2 comes with an embedded web server. You can do, for example, if you open this file and you run this command, which is the equal uppercase H, it will open the web server and it will start the web user interface, which is by default is based in Material. You have the disassembling here, xdump, the super for debugger, functions. You should analyze symbols first, etc. So this is the default interface for the Android application. And there is a work in progress project which is basically implementing a high-level API on top of R2 pipe. Just taking a description of the API and which command maps to this logic thing, and you get a high-level API. You don't have to remember the commands, and you have the completion. And as I said, by plugins and packages, there is support for Frida, support for Keystone, Unicorn, K-Tage Struct Visualizer, Yara, Reddex, Snowman, and there are many other web user interfaces that you can install separately from the core project. About documentation, the project is fully documented in C. If you know C, you can read, understand what any command is doing. There is many people in the IRC that you can speak to them and get some feedback if you have questions. I mean, in fact, there is people that doesn't know how to use Radar 2 and they are using it just because they ask in English and they get comments in exchange. There is two official books. One of them was for Radar 1 and the new one is for Radar 2, which is basically the same but updated for the changes in Radar 2. There are many code snippets and examples that you can look in different repositories and in the internet. There is a lot of test suite that you can read and see all the comments that are and how to use them. There are also several talks and presentations that you can find in YouTube. There is an official blog post, but there is so many other people posting in their blogs things that they are doing with this tool. And now there is also a front end in Qt. My friend Hugo Teso released 2 days ago the Yaito, which is this graphical application. It's basically a front end, a dummy front end that is using the logic of R2 in the background. So it's spawning one instance of Radar 2 using the API and having a nice front end for managing this. So for people who's starting to use, it's nicer because they don't have to remember or to type comments to do things. But if you want to use all the power of the tool, you will have to use the command line, mainly because it's impossible that a graphical application can implement all the logic of the command line tool. So, for example, all the power of Unix cannot be expressed in graphical applications because you cannot pipe Windows, for example. So let's go practice. To start with, I got the firmware for this device, and this firmware so here's the firmware. I will load it without parsing the headers, mainly because I wrote a plugin that I will show later. This is the content of the file. At the beginning, there is like 100 in hexadecimal bytes, which is the header. We see that there is some kind of difference between the beginning because there's like a lot of Fs that are specifying that this is clearly different. Then there is a lot of random bytes, and if we go at the end just by pressing the uppercase G, we will see that there is a footer. It's also full of Fs, and at the end there is a footer message which is output bin data end. So that's quite clear that this file contains a header and a footer. Both of them are of size 100 in hexadecimal, so we can dump what is not the header to a file and then analyze that. So to do that, we will use the what the fuck command, which is write to file. This command accepts two parameters. The first one is the file name, and the second one is the length of the data that you want to dump. So we will dump this into dump firmware.bin, and then we will specify the size. The size is the $s, which is the variable that means that is this file size, and we will subtract 200 in hexadecimal, and then we will use the at modifier, which is making a temporal seek. So when you use the at character in Rudder2 command line, Rudder2 will seek to this address, and then we'll run the command, and then we'll seek back to the original offset. So we will run this at this offset. So here is the final dump. As we can see, there is this number, which is the number of bytes that have been dumped. If we print the header of the firmware using pxbb, as I said, px is xdump, but if we use the B modifier of the xdump, we will interpret the words or 4-byte words in little endian. You can specify big endian or little endian just by changing this variable. But it will interpret each 4-byte wide words in hexadecimal. So here you can see that there are a bunch of numbers, and after some Fs we see that there are two numbers. The first one looks like an address in memory, and the second one looks like the size that we have dumped before. So looks like this header information is used by the flasher or by the bootloader or by somebody that we don't know yet, who is mapping who is specifying how many bytes and where must be written to the target device. Okay, so we have dumped the dump firmware here, so we will load that. There is no header special thing in there, and we can see that this is just random data. If we can scroll down, we can try to disassemble this. In visual mode, if you press P, you will jump into different print modes. And as I said before, this is an ARM. So by default, it's loading the local architecture. So this is 686 laptop. So we can change the architecture using this command, which is e space asm.arch, and then you can specify ARM. And we can do the same with bits, which specifies that this is Thumb is not really a 16-bit architecture, but it's a 32-bit. But for differentiating, because in Thumb you can switch between ARM and Thumb mode, so I use the ASM bits variable to switch between 16 and 32, depending on the Thumb or not. So here we have the disassembly in ARM. If we scroll down, and well, if you know a little bit of ARM, you will see that this is not real code. I mean, there are some jumps in there, but most of them makes no sense. There are a lot of invalid instructions. So we can assume, and all the references, for example, here are not valid. I mean, those are addresses that makes no sense. So we can use other commands to visualize the contents of this file. In order to decrypt the image, we'll have to use different tools. So for example, the MD380 tools repository contains some tools, and some of them are used for decrypting this. The key that they are using for decrypting is basically a short between the original image and the decrypted image. And you can grab the decrypted image if you can dump the firmware from inside the device. I will go later on this. So what we are going to do is use Rahash, which is a tool that comes with Rudder2 and allows you to compute hashes or also encode in different bases like base64, and also use crypto algorithms for encrypting data or decrypting data. What we're going to do here is just using short for decrypting this file. So to do that, we will use the Rahash2 -a short, and then the -s, uppercase E for specifying that this is for crypto, and then the uppercase S to specify the key. as long as it's a big file, we will use the standard input, so we will use just a dash, and we will pipe to standard input this file. So the original file will be the firmware, well, the damped firmware, and the file that we want to compare is the decrypted firmware, because you can find this online. So if you run this, you will get like a lot of trash in the terminal, but it seems like it's a repeated pattern. You see that it's always repeating the same characters. You can easily visualize that using xdamp, for example. And if we search for a specific pattern, so maybe 6 and O, and we press N, you will see that the offset is incremental in a fixed size. So this means that they are using short, and the key is cyclic. So they are repeating the same, encrypting different blocks of this size using the same key. So you can use rahash2 in order to decrypt the file. We have extracted the key also. We will visualize the new file. So as long as we have been able to decrypt this, we can see that here at the beginning there is some random data, but if we scroll down, we will see that this assembly makes more sense in here. I mean, all the offsets and the memory references are quite more meaningful than before. And the jumps make sense. The function preludes also make sense, so you know where the function begins, where the function ends, and so on. So we can say that now the code is already clear. It's not encrypted. But we want to get some information for that, because there is no headers. I mean, this binary doesn't contain any kind of information about where are the symbols, where are the functions, where is the text, etc. So to do that, Rudder2 provides different tools and comments for analyzing information for that. And one of them is PXA, uppercase A, which basically it does that. It takes each instruction of the disassembly and shows one character or two characters in order to show like a block information. You can also press PP in visual mode, and you will get like a map of all the instruction types that are in the binary. So you can quickly see that at the beginning there are some kind of instructions that are some kind of pointers or some kind of data, because this is not real code. At the middle there is some real code, and at the end there is some trash. I mean, there is some random data that is not really doesn't really look like code. You can use uppercase R for changing the color palette if it doesn't fit or doesn't look good in your screen. And then we will compute the entropy of the file in order to get information about which kind of the level of entropy of different blocks in the file. So to do that, we will use rahash2, and we will specify that we want to get the entropy, because entropy is not really a hash, but as long as the input is the same and the output can be assumed or used as the same, I'm not creating a different tool for doing the same. So I'm trying to reuse the same logic or the same tools in order to provide different tools. The uppercase B shows the size of the block that we want to hash, and that we want to hash every block and show the results of that, and minus B will show the size of this. So we will do that, and for example, here is for the bootloader. We will see that the entropy is getting higher at the end. At the beginning is lower, but none of them is reaching 100% of entropy. We can also do the same with the firmware. And you can see that there is, for example, in here, there is a lot of zeros, or places where the entropy is really low, which means it's a repeated character, like maybe 0. And there are other places which is low entropy, and other places which is high entropy. The low entropy, it's used to be when it's text, or plain text, or English text, for example. And when the entropy is high, it's usually code. And if it's really high, it's encrypted. There are other comments for doing that, and we can do that from inside Rudder2. Those comments are the p equal, that allows you to do different analysis on the contents of the file. So you can use, for example, this for showing the entropy, like we displayed before. but with colors and inside router 2. There is also, you can also do the same, computing, for example, the number of jumps that are inside the binary. So by each block, it counts a number of jump instructions that are in the block. So you see that at the end, there are few jumps, and if you go up, you will see that there are more jumps. So you can use this kind of metrics in order to understand where is the data, where is the code, and create some sections, and not need to read the whole disassembly in order to identify all these kind of sections. So one of the things that are more interesting when you're doing reverse engineering is extracting the strings that are inside the binary. If they are not encrypted, you will see them in clear text. What most people do is using the GNU strings program, which is not recommended. At least I will not recommend to do that, mainly because there are some remote code execution vulnerabilities for this tool. Also, it's not able to catch all the strings, not all the encodings. So I built Robin2-Z, which is a command line flag that allows you to extract the strings from the binary. And it's able to detect ASCII, white char, UTF-8, and also base64 strings. So if we do that, we'll do that on the firmware, and we'll see that there are many strings in here. So there is some trash in there at the end. Like this, we can specify that we want to filter strings bigger than a specific length, but what we want to do here is that we will only grab for the white strings, because the strings that matter in this firmware are in this encoding. So grabbing by this, we can see that there is some kanjis in Chinese that are inside the binary. We do the same with the strings. We will see that there is nothing of that. It's a lot of trash, but there is no kanjis at all. So it's not able to catch all these strings. So the reason for finding strings is in order to, you have some clear text in English and you want to know who is using these strings. So if you have like some kind of menus in the device and you want to know who is using these menus, you can just look for the references to these strings and you will know which code is managing the menus, for example. Another important thing when reverse engineering firmwares is that you want to find the base address of the binary, mainly because you have to map all the binaries in memory in order to get all correct disassembly of the program. So you basically need to identify where the code is supposed to be loaded in memory. To do that, there are different techniques. At the end, you will have to map something like that. The Cortex peripherals are mapped in addresses starting by E. The flash memory is starting at 08. There is EO serial ports mapped at 4. There is a secondary RAM which is mapped at addresses starting by 1, but the main RAM is at 2. The difference between these two RAMs is that the fast TC RAM is like twice or 3 times faster than the other one, but it doesn't support executing code from there. So it's useful for some kind of things, but it's not useful for running code, for example. So how do you find the base address of the image that you are analyzing? Well, if you can use different techniques for that. You can use, for example, reading the disassembly. If you map this in memory, you can scroll down and you will see that there are some memory references that are loading a D word. This is 4 bytes from this address. And by reading the 4 bytes of this address, you will see that there is an offset in there. And you will see that this offset is repeated pretty frequently if you scroll down. So you will see that most of the references are data from inside the same page of memory. This allows you to understand that the base address of this image will be 0800 and then C000. So using this, you know where is this mapped. You can do the same with jailbreak, which is the bootloader, the jailbreak and bootloader. And well, I will use that. I have to specify the architecture. And we can also specify the base address, the map address that we want to map this. So here we have like meaningful addresses. So for example, this is a reference to the RAM. There are also other addresses which are referencing data, etc. Another way for finding this is that extracting strings from the binary. Sometimes the bootloader gives you some hints for that. So using grab_into -q on the bootloader, we can grab for, and we get like, there are two strings which are called kernel flash, and you get the base address that I shown before, and the size, etc. For loading the image, as I said before, you can just use the -m command line flag. But this is not enough. I mean, just specifying the architecture and the bits of the architecture and the base address is not enough. It's just very basic loading for reading text, and this is what most people do. So we are missing a lot of things here. The first thing that we are missing is that the CPU is not just a Thumb2 architecture, it's also a Cortex CPU. Cortex implies that it supports different instructions, so you have to specify that you want to disassemble in Cortex mode. So to do that, you will load the image like this, and we will have to change the CPU. In order to change the CPU, you have to use the easm.cpu equal to Cortex. We'll see that the disassembly is quite similar to the other one. The main difference is that if you disassemble Cortex code without Cortex disassembler, you will get invalid instructions for all the instructions that are meaningful. By meaningful, I mean that all the crypto stuff will be recognized as invalid. All the instructions that are enabling and disabling the interrupts will be also displayed as invalid instructions. So if you disassemble the whole text, the whole binary without Cortex, and you grab only for the instructions that are invalid, you will quickly see which are the places that are those interesting instructions. Another thing that we have to set up is the two RAM regions. I wrote a script which is called load, and this script is setting up all these things. I will upload the script later, so you will read it. It's so you can basically use the O command for opening a malloc file, which is basically a fake file that is using malloc for allocating the contents, and it's read-write. So I'm loading two different RAMs and loading also where the mapped devices are loaded. Where the Cortex peripherals are mapped. I'm setting up the CPU, I'm also setting up the bootloader, also setting up the firmware image, etc. And after running this file, we can run it like this, you will get the prompt, and you will get that it's disassembling it properly. But you have all the sections mapped in the proper places. You can use Python, C, Node.js, any language for emulating syscalls. You can do the same for emulating memory mapped devices, etc. So you can later implement all the traces, or you can emulate some part of the code using a SIL, and if this code is using some external devices, you will get that. Another things that are interesting is that you want to filter the hits that are aligned to 4 bytes, mainly because you want to have hits that match at offsets that are mod by 4 equals to 0. And there are also other hints in here that you will see in the script that if you're interested, you can check that later. So, as I said before, well, there is no, some of the Cortex instructions can be interesting to check. This is the difference between the non-Cortex disassembly and the Cortex disassembly, which is using the MRS and MSR instructions for enabling and disabling the interrupts. You can use code analysis, so we do, for example, we load the jailbreak, and we do like AAC for looking for all the calls that are in the binary, and we assume that the destination of a call will be always a function. It will identify 286 functions. So we can go into visual mode, we can seek into the first function, like sim.func. We go into visual mode, and if we press a space, we will get the graph view. We can also press the N key for going to the next and the previous function. We make the font smaller so you can see the whole graph. Using this, you can easily see where is the which functions are more complex, or which functions follow some kind of patterns which are handy for understanding what they are doing. So some of these patterns are this one. So you can search, for example, for some kind of specific instructions, like here I'm looking for instructions that are comparing. When you are looking for that, you will get a list like that. And if you read that, you will see that from this offset, there are a lot of instructions that are taking 1 byte. And if you read the code, you will see that there is like some kind of tree, because it's checking 1 byte and it's checking against different values. So this is all the code which is managing the USB code, all the commands that are sent by USB. For jailbreaking, I will use radif2, which is another tool that allows you to find differences into binaries. I will use the bootloader and the jailbroken file, and we will see that in this offset there is 1 byte that changes. So to do that, I will open the bootloader. I will seek in this address, and if you go into visual mode and change the architecture, you will see that this address contains the 55 number, which is the hexadecimal value that is moving into the R0 register. And for jailbreaking, so if you download the jailbroken bootloader, you will see that the only change is this. To do that, we can enable the io.catch, and this allows you to modify the binary in memory. So the changes that you will do here will not be modified in file. So now that you are using the cursor, which allows you to, for example, follow jumps and things like that, we can use this to modify the value. So we can modify that to be AA. And we can also do that for changing the jump destination. So if you want to change some logic in the program, you can just change the value of the byte using these keys. For dumping the DFU, which is one of the protocols that is using the bootloader for reading and writing the firmware, there is a script in Python inside the MD380 tools repository that implements this protocol. You can only do that with a jailbroken bootloader. So the thing is that I basically took the script, which is in here. So here there are 2 plugins that I wrote for this talk. One of them is the io.dfu, which allows you, it's like an example of how to use Python for writing IO plugins. So here you have like it's a function that returns, so you register the IO plugin, send into a function that is returning this structure, which is basically an object describing the plugin, and then you have some callbacks that will be using the Python API for reading, writing, memory, etc. This is just a proof of concept. I mean, I don't have the device for testing that, but if anyone wants to play with that, it will help you to read the device memory and modify it in real time without having to dump the entire dump of the memory or the firmware and then flash it back. You can do that only for a few specific regions. Okay, so in order to identify where the functions are, there are so many comments in order to. It's not just automatic analysis and you will get everything done by default. Depending on the architecture, depending on the target, you will have to use different comments. So the first thing that people use is using R2 minus uppercase A, which is running the AA command. If you run this, it will analyze all the functions starting on every symbol which is exported by Rabin. But as long as this is a firmware, there are no symbols, so you will have to use another command. So AAA runs the same thing as the AA, but also analyzes all the text section looking for calls. And there are also AAAA, which is doing more analysis on that. So at the end, you have so many commands for extending the basic analysis, but this doesn't mean it to be correct. There is, for example, a lower level primitive like AB, which allows you to analyze a basic block. There is AF, which allows you to analyze a function and extract all the basic blocks of that. You can use AFR, which is an analysis function in a recursive way that it's following the calls. And there are commands like AAB, which is a really blazing fast algorithm that has been implemented by the Fragger. Well, it's a guy from Germany who implemented this algorithm, and it's really interesting, which is basically looking for the basic blocks and then analyzing the graph of all the basic blocks to identify the beginning of all the functions. So it's like 10 times or more than, or 20 times faster than any normal analysis.
There is also AIR, which is basically analyzing the references. And if you do the same with E, you will emulate all the code in a linear way in order to identify the destinations of computed instructions. So for example, if you have a pointer to data that is computed by 2 or 3 instructions, because it's shifting some bits or doing things like that, you will finally get the final value. Okay, so after all this, you will have like a self-analyzed firmware, and you want to close this firmware, or you want to close your R2 session, and you want to load it maybe tomorrow, or maybe load another firmware, and you want to reuse the same information. So one of the things that you can do for that is using signatures. The Z key command was chosen because the S1 was already taken. So this is why they're called signatures. These signatures are basically a way for defining a pattern or a signature for each function in the binary. So after analyzing all the functions, you can get the matching string, which can be, for example, a stream of bytes with a mask. But there is also another kind of signatures, which are based on analysis. So you have some bunch of metrics like the number of calls, the references, the basic blocks, the edges, etc. And you can do that for looking for the same functions in another binary. So this way you can diff pretty quickly and identify where are the interesting points in different versions of the firmware. Here's a quick demo. I don't want to go out of time, but you basically use the Z command in order to analyze all the functions. And you can do that and then pipe all the functions to, as I said before, that there is the asterisk after the comments that will run print the output as comments in Rudder2. So you can export all the function signatures as Rudder2 comments and put them in a file. And after that, you can count the number of all the signatures using the internal grep, which is the sign, and using the question mark at the end after the grep. It means that it will count how many hits are happening with that. So this will count how many lines of the output of the Z command are matching graph, and the other one will do the same for bytes. So we can then later load the signatures and use the Z/ command for searching for signatures. So as you can see, there is some patterns which are repeated, like the slash is used for searching, the asterisk is used for exporting information in Rudder2 comments, etc. And well, this has been implemented for a long time, but Nibble did a complete rewrite of all the implementation, which is quite faster, and there is also support for Flirt, but Flirt is the closest source file format. It's quite only limited to array of bytes with masks, so it's not able to identify functions by metrics, etc. So I'm not really interested in supporting Flirt at all, and just for having like a way for importing these signatures into Rudder2. Also, as I said, all the comments can export information in Rudder2 comments, and there are some of this information which are quite heavy, like all the references, which are stored in SDB, which is a database some kind of Berkeley DB database. It's basically a key value database that allows you to work in memory and also in disk. And the projects will dump all this output into a file in your home directory. So you will have a directory for each project. And when you are loading this project, Rudder2 will basically interpret all the scripts and load the files. Looking for string references is quite important. I mean, we have extracted the strings, but we want to get the references of them. So we look, for example, for the USB mode string in the bootloader. This string is in this offset. So what we will do is seek to the same address, but changing only the 4 lower bytes to 5528. Because we are loading this image in this address. So using the s ... command allows you to make like a seek that changes the lower bits of the address. And using the /b command, we will do a search of all the D words that match the current address. So $$ is an alias for the current offset. So doing that, we will get that we will search for the 08005528, and there is only one match for this string, and this is in this offset. If we use the px_b, as I said before, you will see that all these D words interpreted as little endian, and we can then use the /r against the offset of this hit to look for references to this address. And we will see that there are two load instructions which are referencing this offset. And there are the two places where this address is used. So this way we can identify all the string references. This is done automatically, but if you want to do or understand how it's happening or where are the strings referenced and how it's constructed, you have to do it like that. You can also do the same for looking for memory mapped devices. I mean, you know, for example, that the memory mapped devices are addresses starting by 4. So you can disassemble the whole binary. You can grep, for example, here, looking for instructions that are of type load, and using grep and brackets, you will only get the offset of the instruction instead of the whole instruction. So what basically this command is doing is printing the disassembly of one instruction without showing the flags, because they will be a bit noisy, on all the addresses that are matching this kind of loads. So after that, you will see that there are a lot of load instructions, but you will easily see that some of them are referencing to OXE. You can just use grep for grepping this, and you will see all the code which is using hardware devices. This is pretty handy because you can easily identify which code of the bootloader is using the serial port or anything like that. And this way you can, yep. So doing that, we will basically identify all the functions, all the addresses of all the devices where we mapped them, and we can look then for references to these offsets. So you can see here that there are a D word in like we had this, references to strings, that we have the same for memory mapped devices. This way we can see that, for example, in the flash protection, well, I put this flag in here because I know what this offset is doing. So there are two functions which are referencing this device. And if we look at the functions, we will see that here's the reference. So here is RDP log, and here's the RDP apply log, and RDP is not logged. And we will see that here is the load instruction, which is referencing this memory address, and the other two will show which flag is in this offset, which is the flash protection bit. For emulating code, we will use, in Rudder 2 we use SIL. For showing that, I will open the bootloader, visual mode, and we go down a little bit. We'll see that there is some real code in there. And pressing uppercase O, we will switch between the disassembly and the SIL expression. A SIL is basically a way for representing any kind of instruction in a string. And these strings are basically a Forth-like language. Some of you will probably know what Forth is. It's basically a very simple stack-based language, programming language, which has been used for bootloaders and firmwares and ancient computers, which I think is the nice language for representing what an instruction is doing. So this way, you can emulate or understand what each instruction is doing. If you want to read what each instruction is doing, you can just enable the describe offset, and you will get a comment on the right side saying what each instruction is doing. But we're interested in emulating. So I'm not an ARM machine, but I can press P again, and I will get the disassembly view, the debugger view, which is showing the stack, the registers, and the disassembly. As long as there is no real stack in here, I will use AAM command, which is initializing the memory of the virtual machine. And we get like initialized registers and the stack. So, okay. So we can then use all the stepping commands or debugging commands to emulate code. Okay, so apart from that, if you are more interested in the project, you can see all the Travis Goodspeed talks that are available on YouTube. You can also read the book of GTFO number 10 assign, and you can also check out all these repositories. And if you're interested in Rudder 2, I would recommend you to check all the contents of Rudder 2. You can Google or you can YouTube for that, because all the talks that we did in RudderCon are uploaded online. There are all the slides, all the exercises for the trainings, everything is in this repository. And yeah, that's more or less my talk. Thanks for listening. There is any question?
Yeah, we got a question. We did one question.
Take the cube.
Can I ask two questions?
Quickly.
Okay, one. How do you keep track of all the little discoveries you make?
Mainly by remembering them or writing scripts that, I mean, you mean for this
it's
project?
Not in the tool. You can't make notations.
Yeah, you can type add comments any place. So if you are here, for example, and you can put the cursor code and then you press the semicolon key, you can then type a comment like hello world, and you will get the comment. Well, this is I should disable the description, otherwise it's shown at right. Or I can just change this to show the comments at right. So here is the hello world. And then you can add any comments anywhere. All these comments are also stored in the projects.
Yeah. Okay. And the other question, is it feasible for a normal person with healthy sleep to use your tools for file recovery where other standard software lets me down?
Well, there is user interface, and you can use that.
And it knows different file systems.
You mean for the comments, or
no? Just inodes, the file system specifications of how it's structured. Does it have knowledge of that?
Yeah, there are some talks and some documentation, and the book explains how all the code is structured. So if you want, there are, for example, examples for how to write plugins. I will upload the code for the plugins that are in there. So if you check this, there is also the bin plugin, which is loading the firmware image, identifying the headers, and so on. And if you check in the code, it's quite structured. So you see that there is.
The short answer is yes, you can.
Yeah.
Sort off. Yeah.